Hi guys, so in this video we're going to be looking at Rayleigh's method of dimensional analysis. Remember in the introduction to this course we said that there are many different ways of handling this. Okay, but in this series we're only going to look at Rayleigh's method and Buckingham's Pi analysis. So by the end of this we hope to be able to solve, or we should be able to solve, and be comfortable handling questions using Rayleigh's method. So what's the big idea behind Rayleigh's method of dimensional analysis? When a physical quantity depends on several variables, okay, so when it depends on several variables, Rayleigh's method assumes that the relationship can be written as a product of the power of those variables. So let's use kinetic energy as an example for instance. Let's say the kinetic energy of a body, okay, from experience, we know that it depends on mass and velocity. But let's assume that for the purpose of this example, we don't know the exact formula of this. So Rayleigh's method assumes that the kinetic energy of that same body is going to be a function of the mass and velocity, where these are products of each other. Okay, so Rayleigh's method works with one product term. So the kinetic energy, if we're solving this with Rayleigh's, will be some constant times mass raised to some power times velocity raised to some power. Okay, is not going to be able to solve for a formula that says, okay, let's say you have a constant times mass raised to some power plus velocity raised to some other power. So it's not going to work this way. Rayleigh's method assumes that you have a product term. So that's what we have here, as a product of the powers of those variables. So it's only when we're able to work with our formula this way then we're able to equate the dimensions and have the expression for what we're looking for in the first place. So the general form of the formula, which could be Q as a function of x, y, z. So this could be anything, okay? A function of x, y, and z could come in many different forms. That same function of x, y, and z could as well be x plus y plus z, or it could also be xy plus root z, or it could also be xy over z squared or cube, right? So the function term here really doesn't tell us much in and of itself, but once we're able to work with Rayleigh's method, then we know that, okay, we have a single product term with a constant, and each and every one of these are multiplied together. So once we get to solving questions, we'll see how this can be applied. So the general procedure to solving questions with Rayleigh's method is to identify the dependent variable. So remember the kinetic energy example we gave earlier. We said that the kinetic energy is a function of mass, that's m, and velocity. Okay, so meaning if we're to look at what variables we'll have kinetic energy, we'll have mass, and we'll have velocity. So step one would be identifying the dependent variable, that's kinetic energy. We've done that. To list the influencing variables, so everything else that is not a dependent variable, it's safe to assume that should be an influencing variable. So that's going to be m and v. Okay, assume product form. So that's what we have here. You translate the function of m and v to look something like it will be a constant times m raised to some power times v raised to some power. Okay, you place the variables with dimensions. We covered this in the dimensional analysis introduction video. You know the dimensions for energy, you know the dimensions for mass, you know the dimensions for velocity. So you're going to have to put those into this product term formula. So you expand, solve the simultaneous equations, and at the end of the day, you have your final relationship. So the answer to your final relationship would be in terms of the powers of each of these influencing variables. So let's say we end up getting a being equal to 3 and b is equal to 1 over 2. This is an example. So our established formula from the beginning was that E of k is going to be k m to the a v squared, v to the v raised to power b. So substituting this, assuming this was what we got as our final answer, would be k m cube root v, since we're raising v to the power of half. So this is just an example, for instance. So this is the general procedure when solving Rayleigh's method, and we'll get on to solving questions now. So example 1, Given that the time period of a pendulum depends on the length of string L and the acceleration due to gravity G, okay, use Rayleigh's method to deduce an expression for the period. So let's see. We have three variables. Three variables in this question here. The time period T. So that's what we're going to do. We're going to list out our variables first. Okay, our period T, the length of string L, and the acceleration due to gravity G. Use Rayleigh's method to deduce an expression for the period. So you know we're dealing with a pendulum of some sorts. So this is held firmly, and the pendulum sort of at some way. So we are trying to find the period of a pendulum. So period is that's tau. So period is the time is time taken and the number of oscillations. So it's how long are you recording for and how many oscillations happened in the time you're recording for. So it's measured in seconds. So the unit is seconds. So we've been able to list our variables. The first step is to identify the dependent variable, that's t. So our period is the variable we're looking for. So that means t is going to be a function of L and G. It's easy to establish that. Since we're looking for the time period t, then our influencing variables are going to be the length of string L. So that's this length over here. L. This length of string, assuming it's going to stay constant and not expand and contract. And acceleration due to gravity G. So that's going to be the weight component acting in. Okay, if it's flat here, it's going to be G acting downwards, or this accelerates here. But these will depend on each other. So acceleration due to gravity G. So that's the first step. Use Rayleigh's method to deduce an expression for the period. So remember what we said. We're going to come up with powers for this. So our dependent variable is going to stay on its own. And we're going to introduce our constants. You know, we're assuming it's a product term. So we're going to say t is equal to k. We're not going to raise k to any power. Because if you have a constant k and you raise it to a power a, it's just going to give you some other constants. Okay? And these don't depend on each other. So we leave constants the way they are. 5 cubes is going to be another number, which is not going to depend on any of our influencing variables here. So we leave constants the way they are. So t is going to be equal to k, L raised to power a, g raised to power b. And that's the first part of our problem. The next step is going to be transforming these to dimensions. So remember we said that t is the time taken and the number of time taken for a single oscillation. Okay, so that's going to be seconds. And the dimension is going to be t for time. Okay, we have to be careful. This is period. This t is for period, and this t is for time, t, the fundamental dimension. L is a length, and that's going to be dimensions L. Okay, and g is acceleration due to gravity. And you know, we're dealing with acceleration, so it's a length per time squared. Acceleration is the change in velocity over time, and velocity is change in distance over time. So you have a distance over time, okay? So that's the general idea. We know that the dimensions for acceleration are L per time squared. Okay, so we've established that. So we're just going to put these into the first formula we set up for our expression. So that's going to be t is going to be equal to k L raised to power a. Remember, g is L per time squared. So L t raised to power -2 squared. So we're going to gather the like terms together. So t is going to be k L raised to power a, times L raised to power b, times t raised to power -2b. So remember our law of indices. Okay, so time is going to be k L raised to power a plus b multiplied by t raised to power negative 2b. So now we're going to do the simultaneous simplification that's going to help us end up with our final equation. Okay, so you know we're looking for the period t. So if we were to be very explicit, since t is the dimension of period only, if I were to write m l t on the left hand side of my expression, it's going to be the same as m raised to power 0, l raised to power 0, t raised to power 1 to be equal to l raised to power a plus b times t raised to power negative 2b. The reason this works is that any number raised to power 0 is going to give me 1, and 1 times t is same thing as t. So when we do it this way, we're able to picture that t is not alone in this sense. We have m raised to power 0 and l raised to power 0. So this is going to be very useful for us. We now want to be able to solve simultaneous equations for our variable exponents, okay? So if we were to equate, so we have L here and L here. There's no M term on our influencing side, so this won't affect us. So what we're going to do now is to equate the indexes of each of the fundamental dimensions. So 0 is going to equal a plus b, and then t, equate the indices. So 1 is going to equal negative 2b. So this is equation 1 and this is equation 2. So we're going to have to solve this simultaneously. So let's solve equation 2 first. Since 1 is equal to negative 2b, then that means b is going to equal negative 1 over 2. Okay? So keep this in mind and we substitute it into our first expression. 0 is equal to a plus b means a is equal to negative b. So since b is negative 1 over 2, that means a is equal to minus 1 over 2, which is just going to be 1 over 2. So from here, we can finish up our expression for our formula. Okay? So the whole idea, or the whole task we had, was to find the powers of the exponents, and we've done exactly that. So we said that a is equal to 1 over 2, and b is equal to negative 1 over 2. So with this, we're just going to throw these guys back into the original product term equation we had at the beginning, which was this over here. So we can now say confidently, okay, so recall the reason k disappeared over here is that the dimensions of a constant is 1. Dimension of any constant is 1. So it won't affect anything. It's easy you can drop it once you've converted to dimensions. Okay? So we'll get back to our original products formula over here. You know, we said t is equal to some constant k, L raised to power a, g raised to power b. So we know what a and b are. So we can see t is equal to k, L raised to power 1 over 2, g raised to power negative 1 over 2. So from indices, we can simplify this further, and this is going to be k root L all over root g. We can as well bring these guys together, and then we'll end up with a nice looking formula for the period. So t is equal to k, the square root of L over g. So this is the advantage of Rayleigh's method of dimensional analysis. So if we were to drop this constant and just look at proportionality, which is what is t proportional to? So t is proportional to the square root of the length of the pendulum divided by the acceleration due to gravity. And to see how powerful this is, if we recall the actual formula for the period of a pendulum, we know that t is 2 pi root L over g. So it has given us the exact formula except for explicitly giving us the constants. So that's the advantage of Rayleigh's method. You get the dependent variable, you have the independent variables, get the dimensions for each of them, equate each individual term to some power, solve for equivalence or across both sides, erase, then bring back your exponents and simplify your expression. So we can see how correct Rayleigh's method ended up being. So we know that T is equal to some constant times root L over G. So let's solve some more questions to get absolutely familiar with this. The drag force on a sphere. Assuming that the drag force on a sphere F depends on the density rho, Q, depends on the density rho, velocity V, and diameter D. Determine an expression for the drag force. So we're dealing with, this is still as a fluid mechanics question, okay? The drag force F. So what's happening here is that we have a ball, an arbitrary ball, let's call this ball, okay, falling through air or some liquid or some fluid, rather. So as it falls this way, you're going to have a drag force opposing the fall of this ball as a result of the viscosity of whatever fluid is falling in, okay? So this is falling in some fluid. You could put a ball bearing in a glass of water and compare it to that of honey and compare the drag forces, and you see it sort of holds still. So you have a ball falling in some arbitrary fluid going this way, so weight acts downward. The drag force due to viscosity acts upwards, and depends on the density rho, velocity V, that's how fast the ball is traveling, and the diameter D. Determine an expression for the drag force. So we're going to do the exact same thing we did when solving for the period of a pendulum. Know that the drag force F of D is going to be some function of rho, V, and D, the diameter. So we know that for Rayleigh's, we're assuming is a single product term of each of the dependent variables. So that means F of D is going to equal some constant K times rho to some power, let's call this A, B to some power B, and diameter to some power C. So we've done the first part of our expression. Determine an expression for the drag force. So now the important thing we're going to have to do is to be careful with the dimensions we're creating. Drag force F of D is a force nonetheless, and then we know that this is mass times acceleration. So that's going to be m L T to the negative 2. Okay, so this is the dimension for force. You can always break it down to the physical interpretation, then divide it to be sure that you're not making a mistake with the dimensions. Okay, rho is a density, so that's mass per volume. So that's going to give us m per L cube. V is velocity, so that's displacement over time. So that's going to give us L per time. Okay. And these are diameter, which is a length. Okay, so that's 2 radius, which is same thing as a length. So that's just straight up L. So we're going to put these back into our equations, and we're going to drop the constant since the dimensions of a constant is 1, of any constant is 1. So FD is m. Okay, so that's m LT to the negative 2 is going to equal called density as m per L cubed, ml to the negative 3 raised to power a. Velocity is length per time raised to b, and this is L raised to c. So we're now going to do a very thorough job of expanding it. So this is going to stay as ml t to the negative 2. This is a force. Expand this. So that's m to the a, L to the minus 3a, L to b, t to the negative b, L to c. So we will have to gather like terms. So m is the only one appearing in this expression. That's m to the a. L, you're going to sum everything together. So that's minus 3a plus b plus c. All right, and t is just to the negative b. So we've done the difficult part of the expression of solving through Rayleigh's method, which is finding the dimensions of every involved variable and making an appropriate substitution. So now we're going to equate to the equivalent on the left hand side and solve simultaneously. Okay, so this is m, this is m. So we know that a is equal to 1. All right, that was okay. So a is equal to 1. Cool. So that's helped us with the first expression. So this is our first expression. You could go on to solve L, but if you see that there's only one other variable involved with T. So doing this first will help us, doing T first before L will help us simplify L first. So we can handle T first with some foresight. So we have -2, so that's the power of T on this side, is equal to -b, meaning that b is equal to 2. So this is equation 2. So we already have the value of a, we already have the value of b. So let's now handle for length. So now that 1 is going to be equal -3a plus b plus c. And we can now substitute the equations, the values for the variables we've got. So 1 is going to equal -3 times 1 plus b, so that's 2, plus c. So handling this, 1 is going to be equal -3 plus 2 plus c. Okay, so this is going to be -1. Okay, so simplifying this, you have 1 plus 3 minus 2 is going to equal c. You really have to be careful with this. Any mistake here will give you the wrong exponent. So this is 4 minus 2, and we know that c is going to equal to expression 3. So to write our variables, our exponents, a is going to be 1, b is going to be 2, and c is going to be 3. So we can now see, we'll soon see the power and the advantage we have when dealing with Rayleigh's method, how much it simplifies the problem. So all we have left to do now is to bring each exponent back into the product term expression. So we said the drag force F of D is equal to some constant K, rho of A, V to the B, D to the C. So we can now substitute this directly. Remember, for your product term expression, your constant always has to be there. Rayleigh's method can't tell you the value of a constant. It helps with proportionality. So when you're doing your equals to, you always have to introduce your constants. So that means my drag force, F of D, is going to equal K times density. We said A is 1. V is going to be, V is raised to power B, so that's V squared. And D is also going to be raised to power. D is also going to be raised to power 2. Okay, C is 2. So D is raised to power 2. So F of D is proportional to rho V squared D squared. And this is how we solve dimensional analysis using Rayleigh's method. So for those that are actually curious as to what the actual formula is, it is actually the drag force is actually equal to half rho V squared C of D times effective area. So if we compare this to the equation we got, we know that rho is the same since this is a 1. V squared is the same since these are both raised to power 2. So half times CD will go together as a constant. So we're writing this to be half CD times rho V squared A. So you can now ask what happens to A. So we know that A is the effective area, and when dealing with a circle, since we're doing the drag force of a sphere, the effective area that the fluid will act upon will be a sphere of area pi r squared. So we know that area is going to be pi r squared. But since we dealt with diameter in this expression is going to be the same as pi d squared over 4. So substituting this, just to verify that Rayleigh gave us the right answer, which is going to be f of d is going to be half cd times rho v squared times pi d squared over 4. If we take this to the other side, f of d would be half cd, bring all the constants out, times pi over 4 times rho v squared d squared. And if we make all of this k, we can see that Rayleigh's method gave us the exact answer. So that's how we use Rayleigh's method to solve questions on dimensional analysis. So before we go, just a quick recap and see what Rayleigh's can do. Rayleigh's method is simple, it's fast, and it's intuitive, and it's good for small problems that you can easily define. So by define, I mean that you can easily state the necessary dependent and independent variables, okay, as we did before, but cannot determine absolutely the numerical constants involved. So we were able to show that the drag force is going to be k rho v squared d squared, but we can't determine the exact value of these constants through Rayleigh's method. But it does help us, very importantly, to come up with an equation of proportionality, which is very important when dealing with physics and fluid mechanics. And it is very difficult to use this for functional forms like trigonometric forms, exponential forms, and logarithmic forms. So if your expression depends on some sort of combination of a variable this way, Rayleigh's method wouldn't be the best for this. You would definitely have to solve it analytically through solving your differential equations, okay? And it cannot easily handle many variables. So if you come up with a long one variable expression that depends on multiple variables, each of them will be raised to power a, b, c, d, e, and f, and you only have 3 fundamental constants. You will end up having more unknowns, more equations than unknowns, more unknowns than equations. Okay, you end up having more variables you have to solve for than you have equations to solve those variables. So it's not well poised for multi really large variable questions. But nonetheless, Rayleigh's method is still very useful for determining proportionality relationships between problems when dealing with fluid mechanics. Okay, after this we'll cover Buckingham's Pi method of dimensional analysis, look at how it differs from Rayleigh's, how it is stronger and can handle many variables, and also reduce our problems to functions of dimensionless terms. Okay, so thanks for watching. If you have any question, please leave them in the comments or post them in the community. Thanks for watching, and I will see you in the next video.